This problem here, it is asked that here is a body. The body, if the body is supposed to be unknown, it is weighing 6 grams when placed in one pan and 24 grams when placed in the other pan of a false balance. Now false balance, we mean that in the bazaar we see this kind of balance. False balance means that this center line is not at the geometric center, it is a bit shifted. So it is asked that the beam is horizontal when both pans are empty, which means that the masses of the two pans must be unequal because lengths are unequal, so the torque must balance out. So true weight of the body is okay. So now we are going to solve this problem. Let's assume that this is the line, and here we have the first pan, here we have the second pan, here is the center line. Let's assume this length is A and this length is B. Okay, let's assume weight is m1 of this pan and this is m2. Now it is asked that the beam is horizontal when both the pans are empty, which means the torques should balance out accordingly. m1a is equal to m2b. Next we have the fact that the body weighs 6 grams when placed in one pan. Now we are assuming A less than B. So if a body is placed here, you need to have a lesser amount of weight here to balance it. That's why it would be weighing 6 grams. This is derived from logic. So because if you assume here, there might be a mistake. So let's do it. Let's put the x mass here. X plus m1a is equal to 6 plus m2b. This is equation number 2. Then it weighs suddenly 24 grams when placed in the other pan. So we will write accordingly. X plus m2b is equal to m1 plus 24 into a. We will now solve these three equations. So we will try to divide with this equation of 2 and 1. So we have accordingly, let's do it. It is x plus m1 by m1 is equal to by m2. From here we get x by m1 is equal to 6 by m2. X is equal to 6 m1 by m2. We'll keep this value. Then we'll use these 1 and 3. Dividing them, we will actually get that I'm directly writing it. 1 plus 24 by m1 is equal to x by m2 plus 1. This will get cancelled out. So we have x is equal to 24 m2 by m1. We'll multiply these two values. X square is equal to 144. Then x is 12 grams. This is the correct answer. Next we have this problem. Here is a platform of mass 40 kilos. The man is standing of 50 kg mass. The man must exert a force to keep the platform in equilibrium. Okay, so let's try to solve the problem. Let's first draw the diagram of this problem. This is fixed over here. This is held by the man, and this is pivoted at the ceiling. So let's assume that the force or the tension exerted required is T. This is also T. This is the same rope. Same rope continues here. This is also T. Then this force on this pivot is 2T. We will now try to draw the free body diagram of this man. So if this is the man, we have mg. Here we have T. And we have the normal reaction also, which is exerted by the platform, right? So for the equilibrium we can write T plus N equals to mg. This is equation number 1. Next up we'll draw the free body diagram of the platform. Normal reaction is upwards in the free body diagram of the man. So by Newton's third law, normal reaction will be downward for the platform. The tension will also be exerted like 2T because it is going to pull it up, and the self weight of the platform, which is mg. Now here students will make some sort of mistake over here, so be careful. So now let's try to again do it. This will also be in equilibrium. 2t is equal to n plus mg. Equation number 2. So I am writing this equation here. 2t is equal to n plus mg. It is better to write this m2. This will get cancelled out. 3t is equal to sum of the masses, which means 90 g. T is equal to 30 g, means 300 newtons, which is the correct answer. Okay. Next we have this problem. It is said that there is a chain which is of mass m. It is attached at 2 points A and B of two fixed walls. The chain is not massless, it has a mass, so there is sag exist. This sag is making some sort of angle theta. So we have these two problems based on the above question. Let's try to draw the diagram. This is the chain. Here it is asked that we have to first find the tensions at the point A and B, and this line must be important. Assume that tension is always along the length of the chain. Here we'll assume tension T. So if this is theta, then this is also theta, then T cos theta, and this is T sin theta. Same diagram can be done at this end also. Then here also we have T sin theta, and this chain has mass mg. So since the chain is not moving around, you can write 2t sin theta is equal to mg. T is equal to half mg cosec theta. Next of the problem is tension along the midpoint of the chain. We can assume that the tension here, let's assume that it is T. Tension will be in the horizontal direction because it is mentioned in the problem along the length of the chain. Now the tension in the wire we calculated it a few moments back as T. If this is T, then this will be T cos theta. This T cos theta component is supposed to balance this T because it is not moving around in this axis also and this axis also. So we have T. It is better to write T0. T0 is equal to T cos theta. So T0 is equal to half mg cosec theta cos theta. Right. Okay, so now we have this problem. It is asked that there is a varying horizontal force F is equal to Bt acts on a block of mass m kept on a smooth horizontal surface. An identical block is kept on the first block. The coefficient of friction between the block is mu, the time after which relative sliding takes place. So let's try to draw the diagram. This is the downward block, this is the upper block. Both are of mass m. This surface is frictionless. Force F is equal to Bt acts on this block. There is coefficient of friction mu between these two surfaces. So for the relative sliding, we solve the question as follows. We draw the free body diagram of the upper block. This is M. This is the force of friction. Let's say F1 due to the frictional coefficient arising. F1 is the only force acting on the upper body, so we can write F1 is equal to ma. If we assume the two bodies are moving together with an acceleration a. Next, we can solve for the lower block also. This is also mass m. As per Newton's third law, if we assume the friction acting in this direction, then we have to write the friction in this direction. This will be same as F1. Here it will be F is equal to Bt. So here we can write that F minus F1 is equal to ma. We substitute the ma for the F1, so we can write by combining the two equations and not adding them. F is equal to 2F1. Here for relative sliding, this friction force must be equal to the limiting value, which is equal to mu mg. Is that correct? So this will be F is equal to 2 mu mg, then Bt, this is 2 mu mg, then T is equal to 2 mu mg by B. This is not supposed to match any of the given options, so none of these. So now we have this problem. It is asked to find the reading of spring balance as shown in figure, but to assume the mass m is in equilibrium. So let's try to solve it. This is the mass 2.5 kg. this is mg, then this is mg sine theta, this is mg cos theta. Here we have the t, the reading of the spring balance, which can be also write as t. So here, if this is 37 degrees, then this is 53, then this is also 37 degrees, then this is 53 degrees. So since the mass m is in equilibrium, these forces must be balanced out. So T is equal to mg cos theta to cos 53. Theta is at 37 degrees, so T is equal to mg cos 37 cos 53. This is 2.5 into 10 into 3 by 5 into 4 by 5. This will get completely cancelled out. The answer is 12 Newton, which is the correct answer. Next we have this problem. Here this is a force F is equal to B to the power minus Ct. It is acting on a particle whose mass is m, velocity is 0 at t equal to 0. We have to find the terminal velocity. So we will try to write the expression. Here is written that F is equal to B e to the power minus Ct e to the power minus Ct. F we can write as ma is equal to B e to the power minus Ct. A is equal to B by m e to the power minus Ct. Here we have to write this as A is equal to dv dt equal to B by m e to the power minus Ct. Here dv is equal to B by m e to the power minus Ct. dt will integrate both sides. This will be integrated from 0 to v because velocity is 0 at t equal to 0. This will get integrated from 0 to t, right? So v is equal to, we can write here it is b by mc e to the power minus t minus 1. You can use the integration formulas to arrive at this conclusion. Then v is equal to minus b by mc 1 minus e to the power minus t. Now here it is asked the terminal velocity, which means that the velocity after a long time. So if I write this vt as minus b by mc 1 minus e to the power minus t and do the limits here as limit t tends to infinity, since this is e to the power minus t, so 1 by infinity will tends to 0. So we have vt is minus b by mc. In other words, velocity terminal is minus b by mc, which is the option D, right? Next we have the last problem. Here it is given that there are two blocks of masses m1 and m2 which are placed in contact with each other on horizontal platform. Coefficient of friction between the two blocks can be assumed to be the same, these and these surfaces. Platform moves in acceleration, force of interaction two blocks is okay. Now you can solve this using the theoretical approach. I am solving using the mathematical approach. Here this is the accelerated frame, so in the inertial frame, to make it into inertial frame, we have to put a pseudo force. For the sake of the simplicity, I am putting the pseudo force on this side. You can also solve the question by putting the pseudo force on this side also. So here ma, and this is ma, this is m1 and this is m2a. Okay, now let's try to do the free body diagrams. This is the m1 mass. Here it is m1a force applied. Here you can give the contact force as T. Body is moving towards this side, so we have the friction F is equal to mu m1g, right? This is the free body of the first. Next we have the second body m2. This is also moving with the m2a force on it. Here also we can say this is the contact force and this is the m2g, mu m2g friction force. Now the two bodies will move with some sort of acceleration. Let's call it ax. So for the sake of the problem, we can write m1a minus t minus mu m1g is equal to m1ax. And for the second one, we can also write m2a plus t minus mu m2g is equal to m2ax, right? So now we can solve this problem by first of all adding the two equations, and we can eliminate the t. So we can get m1 plus m2 into a minus mu g into m1 plus m2 is equal to m1 plus m2 ax. This term is common, we are cancelling this out. Then ax is equal to a minus mu g. We'll put this aside. Now we'll use one of the two equations and substitute the value of ax. Then we can say m1a minus t minus mu m1g is equal to m1a minus m1 mu g. This and this gets cancelled, this and this gets cancelled, so t equal to 0. So for all values of m1 and m2, we have shown that the tension, I mean the force of interaction, is 0 in all cases. So option A is the correct answer.